Hello, my name is Justus ICCMA23. Welcome to the ICCMA 2023. Today I'm going to be talking about a paper we worked during the summer, an interesting paper. The title of the paper is Online Self-Optimizing Posicast Controller Framework for Smart Process Control. The co-author for this paper is Dr. Jairo Viola and Dr. Yantuan Chen, and it's going to be using Merced Mesolab. Okay, so the outline for my paper, I'm going to start with motivation. The motivation is going to be on Posicast control. I'm going to introduce self-optimizing control framework. And then the case study for this work is going to be a flyback converter, power converter system, and then the conclusion and future work. So what is the motivation for this work? Gas control is a classic control technique developed by Professor Smith in the 20th century to solve the oscillatory behavior of underdamped dynamic systems with manageable overshoot, which is captured in this paper here. So consider this problem. I'm trying to move this pendulum from this initial position to the final position. And when I get to this final position, I do not want any oscillation. Now, this problem is meant to reflect the behavior of underdamped systems so that when you're able to solve this problem, you can apply the same philosophy on underdamped system. So how did Professor Smith come up with a solution for this problem? So here it is. Used what I call the feed-forward Posicast. So what is a feed-forward Posicast? Basically, the input to your system, you delay the input. So you have the first input and then you delay the second input based on the half period of your overshoot. So I have my original system has an overshoot, and the half period of that very first overshoot will decide the period of my delay of my input. Okay, so that's what I do. So how does this work? So when I send my first input, at that half period, the system begins to oscillate. And then at that point, I send my second input, and then that's when it gets to the final position, the oscillation at the final position cancels the oscillation that is started from this very first oscillation that is started at the half period. And that is how I'm able to cancel that overshoot of my system. So this is the original system here, and that is the Posicast feed-forward Posicast control system. Now, it was found that the feed-forward Posicast control is subject to parametric uncertainty. So when there is a parametric change in my system, it's much difficult to tune my Posicast controller. To solve that problem, we use the feedback control system. This is a feedback control structure. In this case, we have my Posicast controller here in a feedback control system to solve the problem of a model uncertainty that affects the Posicast controller. Now, even though I do have my Posicast controller, I still need to find the optimal parameter like the delta and the TD for my Posicast control, and also have to find the optimal parameter for my controller in real time. How do I do that? This is the contribution of this paper. The main contribution of this paper is the assembly of an online self-optimizing Posicast controller based on the closed-loop Posicast framework and the GCNM optimization algorithm to improve the robustness of a varying and highly oscillatory system. So basically, I have my Posicast controller system and I have my controller. Okay, so my Posicast is my filter, of course, and then my controller. And I'm trying to find the best gains for my Posicast and for my controller using a self-optimizing controller framework in order to find the best gains in real time online. So this is the contribution of the paper. What is the configuration of my self-optimizing controller? So my self-optimizing controller is this section that I have right here. Of course, this is my controller. In this case, it would be like a PI controller, and this is my Posicast filter right here, and this is my plant, in this case, the flyback converter or power converter system. The configuration of my self-optimizing control, of course, what I'm using is called a globalized constraint Neldermead, which I will introduce in the slides ahead. Right? It comprises of having a cost function. Okay, so this is an optimal control problem here. So I have a cost function. I'm trying to minimize this cost function, and my cost function I'm trying to minimize the overshoot, the settling time, and the error. And these are the weights that I put on my cost function. And this is subject to this constraint. The constraint is Kp, Ki, delta, and Td. So Kp, Ki is the constraint on my controller, of course, and then delta and Td is the constraint on my Posicast filter. Okay, so next, how does this globalized constrained Neldermid. How does this algorithm works? This is a Neldermid algorithm. What is a Neldermid algorithm? A Neldermid algorithm is gradient free optimization algorithm. How does it work? It works based on this principle here. So it generates n number of points in order to search the cost function space in order to find the minimum cost function. So first of all, it generates n number of points. So let's say it generates 3 points. It performs reflection of the points to find the minimum. If it finds the minimum, it stops that and it picks that minimum. If it doesn't find the minimum after reflection, it does expansion. If it doesn't find the best after expansion, it does contraction. If it doesn't find the best after contraction, it does shrinking. And then if it doesn't find the best after shrinking, it restarts. So that's what we call probabilistic restart. It restarts the search in order to find the best point, the minimum point of the cost function before it moves to the next thing. Okay, so this is the operation of the globalized constrained Neldermid, which is different from Neldermid because the globalized constrained Neldermid has that option of restarting, so it is not stuck in a global minima. Okay, that is the advantages of the globalized constrained Neldermid. Okay, so now let me introduce to you my case study. It's going to be an ideal flyback converter. This is an ideal flyback converter configuration that I have here. So how does it work? So I have a switch. This is a MOSFET switch. Okay, and this MOSFET switch is operated using a PWM on and off. And so how does this flyback converter work? So based on and off of this MOSFET, the flux of this transformer is changed. So based on Faraday's laws of magnetism, changing flux induces voltage on the primary side of the transformer. And this induced voltage on the primary side of the transformer is reflected on the secondary side of the transformer based on this number of windings of the transformer. And this reflected voltage on the secondary side of the transformer is captured in this load right here. This is a diode that I have here. It's captured in this load right here. And so this is the basic operation of the flyback converter. Now, in order to use this flyback converter, I have to be able to extract the transfer function, which is a mathematical representation of the input to the output. Okay, so in order to do that, there's a well-defined method called the parametric AC averaging technique that is being used to derive the transfer function of my flyback converter. What is this technique? So this technique is done by first deriving a flyback converter equation from conservative laws, okay, add small perturbation to the constitutive equation, apply Taylor series, obtain the DC, linear AC and nonlinear AC, define the state space, obtain the average state space, linearize the average state space. So here's the steps. Okay, so first of all, step one, derive the flyback equation from conservative laws. Okay, so Kirchhoff voltage law, Kirchhoff current law. So we analyze the flyback when the MOSFET is on, and then we apply KCL here, Kirchhoff current law, and Kirchhoff voltage law. Apply KCL at the nodes, apply KVL around the loop of the system. So from which we obtain this equation here for when the MOSFET is on and when the MOSFET is off. We obtain this equation here applying those laws. Step two, we apply perturbation average to the states. So for each of the states in step one, I apply this perturbation average and I add both the on and the off period to obtain these equations that I have here. Then continue through to step 7. We can follow this. If you're interested, you can follow this paper right here. It outlines all the steps in the paper. Okay, so and then we get to the very last step, step 7, where we linearize the average state space model around a duty cycle. When we do that, we're able to obtain this equation here, these two equations here. This is the transfer function equation from duty cycle to state, and this is from duty cycle to the output. We are more interested in this one here. So these are the parameters that I use for my system. I apply these parameters to this equation to obtain this equation. This is the equation of my flyback converter. This is my case study equation. If you notice, the numerator of this equation have zeros that are in the right half plane of a root locus plot. That means that the system is a non-minimum phase system. What are the characteristics of a non-minimum phase system? For a non-minimum phase system, it has reduced phase margin. That's a stability issue. It has undershoot and it has consistent oscillations. So this is what I mean here. So for this flyback converter, you can see this is a step response of the system. It has sustained oscillation. Although the system is not unstable, it's still stable. It has oscillation, and it also has undershoot because it's responding opposite. So I wanted a step, but it's going opposite of that. So it has undershoot. And as you can see from the body plot, you can see it has reduced phase margin. So this system is difficult to control. However, implement my setup. So this is my setup. I have my controller, my PI controller, my Posicast filter, my flyback converter, which I just obtained, and then my self-optimizing control on top in order to find the best parameters for my controller and for my filter. So here are my results. For the first result, what we did first was, before we did any parametric change on the flyback converter, we used a flyback converter with a capacitor of 100 microfarad. So as you can see here, this is the response of the system here. Now, as you can see from this response, the system goes from 0 to 0.2 seconds. Okay, at 0.02 seconds, right, between 0.02 seconds and 0.024 seconds, the system is searching for the best parameter in order to converge to. So it's searching for the optimal KP, the optimal KI, the optimal delta, the optimal TD. So this is what my globalized constraint nail-the-meat is doing, searching for the best parameter. At this point here, this is the initialization. And after 0.1 seconds, at this point here, 0.1 and 0.16, which is this plot here, is able to find the best parameter. As you can see here, it converges the best parameter, and it's able to kill that overshoot. As you can see, the overshoot here before it finds the best parameter, and this is after it finds the best parameter. It converges. Both the cost function converges, optimal overshoot, and everything converges. Next, I do the parametric change. So I want you to look on this plot here. This is where you can see the parametric change. On here, this is when I have the capacitor is 100 microfarad. This is when it's 200, and this is when it's 300. As you can see, the cost function changes because it's trying to find the optimal cost function for the changes in my parameter, right? And also you can see it here in the settling time. It changes, right, because of the changing parameter. So from my final result, of course, it is initializing in order to find the best parameter, and then it eventually converges to the best KP, the best KI, the best delta, and the best TD. Now you cannot see on this search on the searching output that I have here, you cannot clearly see the changes in the parameter, but you can see it here. But the system is able to converge and kill the overshoot and maintain a smooth transition in killing the overshoot, even though I'm changing the parameter from 100 microfarad, 200 microfarad to 300 microfarad. Finally, we did, in order to see the adaptive ability of the SoC, right? What we did, we ran 30 simulations, 30 iterations with 100 microfarad in order to see how KP, KI, delta, and TD changes. And we can see the variability of those parameters is not much, it's quite small. It shows that the SoC is quite adaptive, and this is the body plot of our system. Okay, so this is the table that shows. So on here, on my table here, you can see the obtained optimal values that I have for capacitor of 100 microfarad. That's my parameter right there. So you can see the KP, the KI, the delta, the TD, and of course, based on these parameters, this is my overshoot and this is my settling time. And this is for the different parametric changes. For the case 1, when I have my 100 microfarad, case 2 with the 200 microfarad, and then case 3 with the 300 microfarad. And of course, these are my KP, KI, delta, and TD for the capacitor variation for my system. Of course, this is the nominal. This is the nominal minimal to the maximum that I need my KP, KI to be, and this is what I finally obtained for my result. Okay. In conclusion, the Posicast framework is suitable definitely for improving the response of highly oscillatory system with parametric uncertainty, okay, which I showed in my obtained result. And it shows that the SoC is also adaptive, right? It's able to adapt because you can have variability of, we performed 30 iterations using the same parameter of 100 microfarad, and we can see the variability of the of the tuning parameters, we can see that there's no much variability, which shows that the SOC is adaptive for different variables. Okay, so our future work will be extending the Posicast controller to a MIMO configuration, more multiple inputs and multiple outputs, and finally implementing the full control structure on an FPGA board. Okay, so thanks for your attention. I will